Okay. And we'll give people just a couple more minutes to show up. Looks like we still have a couple people popping in. Everybody ready for Thanksgiving?
Not even close. I have to take off next week just to do some honeydews. Right after this, I have to repaint a bathroom because it's not the right color blue.
That sounds like a total honeydew thing, yeah.
Are you telling me that there are more than 16 colors? Is that what I'm hearing here?
Yeah, yeah.
I thought there were
What's
only
that?
4
The EGA
colors.
palette?
I think that was wasn't it the VGA? Oh, it was the Windows palette.
No, it was it was EGA.
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 Yeah,
I mean,
VGA went to 256 if I remember right, and then up from there.
there is one blue, and then there's cyan, and that's it.
All right.
I know somebody that would disagree with you. I live with her.
Yeah, my wife as well, just if it's any consolation.
Yep. All right. Go ahead and share a screen here and we will start. Let's see. Okay. Whoops. So folks, welcome to the November 2023 meeting for the Seattle Robotics Society. Steve is still out for a little bit, got something else going on during this meeting time, so I'm running them. If anybody else would like to help out, let us know, just in case I'm not available. Oops, here. Okay, video is provided by Zoom. We are recording these meetings, and we will post them on YouTube shortly. And let's see. Yeah, you guys pretty much all know this slide. So please mute your microphone unless you're actively sharing. This keeps the noise down. You can use the Zoom chat to ask any questions, make comments, post links, and all the chat information will also be posted with the video. Let's see. I just kind of mentioned this. Lloyd and various others will host the meetings for a little while via Zoom. Yep, that should be kind of obvious by now since I'm here and Steve isn't. We do need some alternate meeting facilitators. So right now, I can keep doing these for a while, but if something does crop up and I'm not available, we do need to get a backup. So please let Steve know at seattleroboticsociety@gmail.com if you would like to help Steve and I keep running these and back me up in case I'm not available. I think Steve's got about 3 or 4 months left with his. It was like a 9-month thing he had going. So he'll be back at some point too. Okay, past events. Anybody have any comments on past events they would like to share? Oh, just go ahead and unmute. Okay, I'm not aware of any either, so we'll just go from there. Local makerspaces, Snowco Makerspace, the libraries, all have makerspaces. There's the Cree Makerspace in Renton. I've been wanting to check that one out, but haven't had time yet. Should do that. Seattle Makerspace, AltSpace Needle, or AltSpace, excuse me, AltSpace Seattle, Seattle North End Makers. Any others people want to throw in there? Okay, we'll move past that one. Let's see. This might be outdated. Does anybody know if RoboGames is still going in Pleasanton, California? I think that already happened. And then Chaz, do you have anything on the war group you want to throw into this one for upcoming events?
Yeah, so yeah, absolutely. Thank you. So I'm sorry, I'm just bringing it up. February 24th, at the same place we did it before in Lake Forest Park. It's a bookstore. It's like 17171 Bothell Way. I can't remember the name of the bookstore off the top of my head, but
Third place books,
Third place.
right?
There we go. Yeah, third place books. Thank you. We're going to have another PopCan challenge. It'll be an SRS PopCan challenge competition. It'll just be the PopCan challenge portion of of all the different types of SRS games because it's indoors. Technically, we could do one of the build challenges if somebody, the indoor one, the first one, if somebody wanted to, test out their robot. But yeah, that's February 24th at 10 a.m. It's posted on there's actually a PopCan challenge meetup. And it's also on Snohomish County Robotics Group as well, which is also another meetup. So a little bit of Googling will get you there, and I could probably send the links in sometime. Actually, I'll post the links here.
Yeah, just drop them into the chat and then
Yep, we'll do.
grab them there. Cool, thanks.
Yeah.
Anybody else have a upcoming event they would like to do a plug for? Okay. Well, I guess it's my turn then to plug Robothon. So we are looking at, we're still planning for next year. So far, what we're thinking is, I should also announce, let me announce this. We have decided we're going to stay with just remote meetings at this point. There wasn't enough interest in going back to an in-person meeting. We had about, I think, a total of 5 people were interested. And we kind of look at how that would work out. Basically, we'd do an in-person meeting with maybe about 2 people in the room, and everybody else would be online. And that's kind of like, that's really not an in-person meeting. So what we're going to do is we're going to tie this together with the events. We still have access to the field house, the First Wa field house. So what we're going to do is probably sometime in the first half of the year, we're going to do a in-person event, and it may be on a Saturday. It maybe we'll figure out. It may be one of these meetings. It may be something different, but basically just an in-person event where we'll do some robot challenges, line maze, walker, whatever, and we'll do that at the field house. We haven't quite figured out exactly what or when that is yet. And then we'll do another, in the second half of the year, we'll do another outdoors event, probably at Sunnycrest Elementary, where we did it last year. And so that's kind of what we've got coming up for Robothon events this year. If folks would like to help out, we're always looking for volunteers on the Robothon committee. So just let me know and I can get you on our posting. And we basically meet for about an hour once a month and hang out, have a little fun, and plan an event. And that's a really old picture of me. I'm gonna have to talk to Steve about that. All right. Steve is also looking for presenters. If you'd like to do a presentation, just let Steve know. Basically, it's Seattle Robotics Society at gmail.com. If you happen to know, getting presenters is actually most of the work of running one of these clubs. I do it for Northwest C++ users group, and about 90% of the time it's chasing presenters. So if you know of anyone, or if you would like to present yourself, just let Steve know, and that really makes his life a lot easier. Let's see. In the case we don't have a presenter available, we've always got the open discussion forums. Steve or myself can host these, or anybody else can. If there's one that you're really passionate about, feel free to let Steve know, and you can host that one. Okay, so here's the presentation plan starting through 2024. I'm the presenter today. In the next hour and a half or so, you'll probably get really tired of listening to me, but, well, somebody's got to do it. Let's see. So in December, we've got Bob Cook on his Robo Magellan robot. And January and February are also filled up. So starting in March, there's open slots. So if you would like to do a presentation, just let us know. As I already mentioned, I'll talk about what we have lost And that's going to be a little history and retrospect on the development practices. And I've really got to get Steve another picture of myself. Okay, post-meeting. Anybody's welcome to hang out after the meeting and continue chatting amongst yourselves. We will stop the recording. I also do have a hard stop today, right at 12, but I can, if people are chatting, I can just turn the meeting over to somebody else, and you guys can keep going as long as you would like. Okay, we're now to the around the room session. And oh, I'm gonna have to thank Steve. He put some videos up there for me, so awesome. Okay, does anyone have anything for around the room? I'm just going to go ahead and release the screen share for the moment. And go ahead and just unmute and go for it.
I wonder if any of y'all watched the Starship SpaceX launch this morning. Figured I would congratulate Gwen. She did a fantastic job of running SpaceX. Won't say anything more about other people. And I just want to point out that the thing that holds the rocket is, I believe, the largest robot that has ever been built, the largest robot arm. It is a Scara robot, right? It has at least 3 degrees of freedom.
This is the chopsticks thing you're talking about, right?
Exactly, right?
Yeah, that's interesting.
It can go up and down. It can go up and down. It can shift left to right, and it can open and close.
Mm-hmm.
So I'm thinking that's a 3DOF robot arm, right? And utterly massive. So worth taking a look at. You can find some video of it online, and generally a very successful launch today. It was very inspiring.
Yeah. Hey, James, did you actually see? I missed I was asleep during the launch. My bad. Have you seen anyone where they
slept?
It's on YouTube.
I know.
You're
It's
dead
5
to me.
a.m. It was 5 a.m. on a Saturday. Come on. I'm a morning person, but let's get real.
I'm just kidding. I totally slept through it as well.
Hey,
It's on YouTube.
Is it on YouTube? Yeah. Okay,
Yeah.
cool.
Yeah, there's so space.com has a very nice just a copy of the SpaceX video, and then I also watched Everyday Astronaut, who did a 3-hour long thing, so you kind of have to see it in order to see. But the upshot of it, if it's worth giving a quick summary of what happened. Yeah, so basically it took off without any problems. Stage 0, in other words, the launch pad didn't appear to take any significant damage. Cameras that were in the immediate vicinity were not knocked over, so that's really good. They have solved the problem of chunks of cement being blown out from underneath the rocket. All 33 engines operated all the way up, and that, by the way, sets a world record for thrust. That's 17.1 million pounds of thrust, 7.6 meganewtons, something like that. I'm not going to remember exactly in science units, but that beats the N1, which was the prior record holder at 10 million pounds, if I'm remembering this correctly. So that's pretty cool. They were able to fly all the way up cleanly, no spurts, no jerks, no problems, very smooth, nice mock diamonds and all of that. And then they did the separation, which is also a first because Starship has to fire. Basically, it lights its engines and pulls away from the first stage, which is, unusual. And it would appear that maybe something was damaged on the top of the booster as a result of that, because then the booster did flip away as it was supposed to. It looked like it was maybe having trouble holding its orientation. And then there were a couple of little bursts where maybe an engine was failing, or maybe I don't know if they were supposed to light engines at that point. I think they were going to do a boost back. So I'm pretty sure they were trying to light engines and they did not light, and so it went. I'm guessing it went off track, and the automatic flight termination system blew it up. But after it had already done its job, um, and then Starship itself continued on, had a nice long flight on up. It looked like maybe the engines cut out a little early, and then not long after that, again, it did a rud. So basically, they blew up both of them. So the news will be full of, Starship blows up, total failure, da 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 da. When in fact, it was a total success. I mean, everything that they wanted out of the flight, they got. They now know that maybe they need to figure out what got damaged on the top of the booster. Ship lit up. They have to figure out what happened. I'm nervous about the tiles on Starship, but in general, huge success. And again, Gwen Shotwell is a hero.
And by the way, folks, talking about rockets, definitely robots, because they really are just they're big fancy robots.
Especially now that they're landing themselves.
Yes, that's things that humans could not possibly do in real time, controlling them. So they are completely autonomous. They're sensing their environment, they're acting on their environment, and so forth. So at least by my decree, they're robots and we can talk about them. How's that?
So the other thing that's in the news today is Sam Altman of OpenAI got fired.
Yep. Yeah, go for it.
Well, it's just
oh, you just okay.
Apparently, Ilya Sutskever staged a coup, if you will. He and Altman apparently did not agree on the way the company was going, and so he got the vote from the board to get Altman removed. And so it'll be interesting to see, because Greg Brockman, who was president, also quit when Sam got fired. So there's a very strong chance that those two will go off because they were good friends and had similar ideas, and recreate what they did at OpenAI and probably push it further.
Yeah.
I saw a headline to the effect that he was fired for lying, but they weren't specific about what he lied about or to whom or anything. So take that with a grain of salt.
Yeah. I thought the phrasing on that was interesting. I think it was repeated lack of candor or something like that.
Lawyer talk.
Yeah, I thought that was entertaining.
Yeah, it may be more that he just didn't tell them what was going on rather than actually actively lying to them.
Yeah.
So I would, this is speculation on my part, but I would guess that the board of directors, being legally responsible for stockholder return, was expecting more profit-making ventures, and that Altman was perhaps more dedicated to open source and building community and things like that, and not in making a buck. But that is absolute 100% pure speculation on my part. The one thing I know for sure is it is a very serious legal thing if a CEO or a board of directors fails to do everything possible to make a profit for stockholders. You can literally go to jail if you make a decision that's good for humanity or society or the country or any of 1,000 other things, but bad for stockholder profits. So my guess is it was around that.
Well, you have to remember that OpenAI was founded as a non-profit organization. So that doesn't seem to make a whole lot of sense, given that.
Yeah, but they have, is it still a nonprofit? I thought they had stock.
I don't think so.
No, I think it is still nonprofit.
Yeah.
Oh, interesting. Okay, well, I retract my guess in that case. I wonder
My speculation was that it was about safety. I mean, wasn't he concerned that we were effectively advancing the technology much faster than our ability to restrain ourselves from doing evil with it. And maybe he wanted to put the brakes on, until safeguards could be put in place.
Well, it's like many other technologies, in safety. TNT was, and nitroglycerin and all that was a great development at the time. But yeah, it's been used for ill also as much as other things. So
I did see that he had just given a talk in which he called for government regulation of AI. And I'm wondering if that rubbed Microsoft at all the wrong way.
well, so many of the CEOs and big people have said, yeah, we got to slow this down. Have you seen one of them do it? They keep pushing it. It's if you don't keep going, somebody else is going to come and eat your lunch.
Yeah. I went to a couple of seminars and stuff in the last 2 weeks on various AI topics. And what's coming down the pike is incredibly fast. Basically, even in the talks, they're making comments to the effect of, if you haven't read the research papers in the last week, you're out of date. The pace of innovation is insanely fast. One of them was put on by NVIDIA. It was NVIDIA LLM Developer Days is one I went to. And the other one was electronic something, EE Times, AI Everywhere. And the pace of development in both the software and hardware aspects it's the fastest I've ever seen. And it's already come to the point where the AIs are feeding back and helping the process along. Yeah, James.
So I just looked this up, and OpenAI was nonprofit up until 2020. They then changed, and investors are allowed to make up to 100 times their initial investment. So I change my status on my suggestion. But I will have to say, I also think that the point about regulation versus non-regulation is that's probably a huge part of it, right? So in other words, he's saying the government should regulate it, and the board is saying, "Ooh, we can't support that because that could potentially cut into profits if we actually did it." As Bob points out, everybody says, "Oh, all the CEOs are basically crying, saying, please don't make us make money this way because this is going to be really bad in the long run." But they're still making money that way.
But can you imagine our U.S. Congress, where most of the members can barely add, subtract, multiply, and divide, trying to make regulations on development and use of AI?
It's their lack of ability to distinguish right from wrong that bothers me.
Yeah, there's that too.
all decisions in government are basically made based on who can quietly give you the most money without pissing off the voting public too much. So there's a decision coming out of that. This ship has sailed, as they say.
But the other aspect of that is, if you look at the government and you look at the various government agencies, not very many of them really want any regulation on AI. DOD certainly does not. I'd bet NSA does not. CIA, no. None of those people want regulations. They want it pushed as far as they can because they're afraid of the competitors.
Well, America's opponents certainly aren't going to regulate it if it would help them against us.
Yeah, I think EU is regulating it, but China and so forth is not, and that's why we're seeing a lot of if you've been following the NVIDIA news, NVIDIA's been heavily curtailed in the chips they can send to China, to the point they're making their own special low power, lower capability chips for the Chinese market directly. So
they're making RISC-V chips now?
No, I don't think it's RISC-V. I think it's the similar technology, but I
just saw an article this morning.
Oh, interesting. Okay, so I have not seen that one yet. No, what I was going down though is that their GPUs, they're making lower clock rate, lower memory bandwidth, and lower CUDA core count versions for the Chinese market to get around the export regulations.
So I don't know. I'm not sure I should mention. Oh, I'm going to go ahead and mention it, but I won't say anything more about it. We should move on. But if you haven't seen the Slaughterbots video, I really recommend you watch that. It's available on YouTube, and I think those things have already started happening. If you look it up, this is being done in Ukraine today, um, and it is going to be done to far greater extent. And as that starts to happen, then you'll see calls for more regulation of AI. But it again, it will absolutely be closing the door after the horses are all out of the barn.
Yeah.
There's no stopping it at this point. But I really recommend watching that video, keeping an open mind about it, because there's like 5 technologies that are required for one of those, and every single one of those technologies is in the open source community.
Mm-hmm.
They are all already out there.
Yeah. Now we're gonna.
Who's
I mean,
over that, Richard?
Oh, go ahead, someone. Okay. So we've seen all this before, where even with the drones, drones came out. They were a wonderful hobby thing, and then we've got people spying in other people's backyards, arming them with weapons, and naming like explosives. Even the little innocuous laser pointer, right? Just reminding people, the laser pointer theoretically isn't a big deal until you stand off the end of a commercial runway and point it at the pilots, which is a really bad idea. So yeah, we're gonna, we've been down this road before. Okay. Yeah, go ahead.
That got dark really quick.
Yeah,
Moving
I was
on.
gonna say.
Moving on.
Let's see.
Before you move on, when are we going to start seeing slaughterbots used to prevent retail theft?
Oh God!
Black Friday, stay in line or else.
Just when you thought it couldn't get darker, Gordon takes it the rest of the way.
Yeah.
Thank you. I lived in the dark.
So I do have a couple of videos we can do if folks would like to do that. Attempting to pull us back into something constructive.
I got one thing to share.
Oh, go for it, Chaz.
And I thought it just to share, just in case you guys are looking for something yourself, but I was building I saw Bob with his sweet Magellan robot hanging out all by itself. So I figured next year definitely can't go by itself. It needs a friend. So I started building a robot. Well, I started designing a Magellan robot. And I was, some of these robots are really expensive, of course. I think Greg, I don't know I can't even imagine how much he spent on his robot. I know I've spent more than a couple $1,000s on mine just through the different iterations. And I felt like that's just too much for somebody trying to build like robot number 1. So I was trying to build something that I felt like what was something somebody could reasonably get some ideas from. And you guys have seen those like electronic circuits where they always use like that weird transistor you can only get in the UK or something like that. And it's just like that one circuit's like pain in the butt to recreate. So I'm like, what kind of robot parts could I use that somebody could reasonably get that are cheap? And I started building something small off like a $20 Amazon frame just to start working on the software, because I knew it was going to take a while to try to pull this off. So I tried to find these things as cheap as I could, and I was successful. And this is a Razor hub motor. So it's a hub motor that you get off those little scooters. I don't know if you guys have seen, they're called hoverboards. They're the things that you step on and they self-balance, and you see all those great videos of people going down on their face on them. And they're somewhere in the range of 300 watt, a little overboard, but I figured, these things got to be e-waste galore, right? And I was right. Matter of fact, they are e-waste galore. They run on 36-volt batteries that go bad in them, and you know, I think if you just watch your local like for free group in your city, I was able to pick up these motors for free. I thought it was going to take me forever to find them for free, but that was totally the right price. They are like a regular BLDC motor where it's like the three wires like you'd see in an RC motor. And you can use RC motor controllers, which are pretty cheap themselves. They have Hall effect sensors, so they have some ability to give you some feedback on where your motor's at, which is great. But on Amazon, I found an actual 400-watt driver for them, and it was pretty cheap. I think it was like $10 or something like that. I can't see it. Ah, stupid thing.
Yeah,
Sorry, I
your
should put
blur
on my
is
blur. Too much
yeah,
Yeah,
blur.
blur is
I could turn off the blur. It's just
you don't mind
my
us
wife.
in behind you? It's not that bad a mess.
Well, my wife it's her mess, not my mess, because we share a. Oh, that's the camera. We share a space. I want no blur. There we go. So it's kind of got these like drivers that have nice heat sinks on them, and you can't really see it too well there, but it's in there. They got terminal strips, so they're super easy to hook up. They actually have um, they have control, and you can actually feed the Hall effect sensors right back into those motor controllers. They're meant for these things, which is great. But they're kind of cool. They have a really big, thick, it's like a 16 millimeter shaft that I just temporarily 3D printed these things. I have a friend that's gonna mill some connectors for me, and I actually plan on in my second version creating an active ride height just to keep the robot level and with the rear end maybe keep it so that it can go in more places if it can change its ride heights and look at above ground. So yeah, it's kind of a cool little motor technology if you guys are looking for a motor. They are heavy, shockingly heavy. I think this thing might come in at 40 pounds, which is a bit heavy. It doesn't need to be that heavy, but I think thankfully the Robo Magellan allows for 50-pound robots, or I'd be in trouble.
Do you have
But
a
yeah,
link for the drivers or the name of the drivers? I'm just
yeah, I'll
trying.
throw the drivers. I'll look it up on eBay because I bought them in here. But
The, the one I'm
gosh,
aware of is O Drive, and they're really expensive.
oh,
But they,
I have some old drives. I would not go that direction. That's definitely above and beyond. And ODrive even has some really cool new ones that are they're single drivers. I have the dual driver, but those are uh those are for people that don't like their money. They just want to throw it away. So that they're cool, they're great. They have a lot of like low speed control, but um it's hundreds and hundreds of dollars for those things. So I think I paid for like four motors, the O drive drivers, the braking resistors, and something else. I think I gave them like $1,200. So you guys don't want to go that route unless you got
how
more
much
money
did
than
you spend on these guys from eBay? How much were they?
yeah, they were like I don't know, they're super cheap. They're like $20 or something like that. Um,
Okay,
I'll I'll
yes,
get
I
a
want that link.
yeah, I'll get a link and drop it in here. But I just felt if you guys were looking for a motor solution that could go out in the grass and have some fun. It's, I mean, it's e-waste and for the most part, and it's something you could pick up and you could throw anywhere between 12 and well, I'm running two 6S batteries into it in series, so I'm running like 46 volts or so somewhere in there into these things, and they take up to 80. So uh, so yeah, I'll get you guys a link for that, and just thought it might be a something fun to build around if you can find them.
yeah, that's cool. Okay, does anyone have anything else? If nothing else, I've got a video we can do. Put this away and okay, hang on a second. Let me share this screen. And I'll have to thank Steve for getting me some videos here that share. Okay. Were you folks able to see that? I just realized okay. Just realized the way it was presenting on my side, I might have had the wrong screen. Now, let's see. Grab this one. All right, we're gonna get an advertisement with this one, but it's okay. Hang on a sec.
When you write, your tone influences how readers respond. With Grammarly, just highlight your text and type how
Here at TRI, we believe robots should amplify people, at home and at work. To achieve this, we conduct cutting-edge research to make robots more flexible, robust, and general purpose. We've had a bit of a breakthrough. Today, TRI is announcing a new method to teach robots dexterous skills quickly and easily. Our approach is built on a powerful generative AI technique called diffusion policy. This allows us to teach robots much faster and with significantly fewer demonstrations. The approach holds great promise for creating what we call large behavior models. Just like large language models have revolutionized chatbots, these behavior models will allow robots to perform useful work in ways never possible before.
Up until now, the majority of robotic manipulation work has focused on pick-and-place style tasks, where a robot is limited to relatively simple sets of objects it's rearranging. Our new approach goes significantly beyond that and lets us explore much closer to the limits of the hardware. TRI's robots are now capable of using tools, pouring liquids, and peeling vegetables. It's exciting to see them engaging with their environments in rich, multifaceted ways, and all achieved without changing any code or explicitly programming any new skills. Using this technique, we've taught over 60 diverse behaviors to our fleet of robots. The process starts with a teacher demonstrating a small set of skills through teleoperation. Then, our AI-based diffusion policy learns in the background over a matter of hours. It's common for us to teach a robot in the afternoon, let it learn overnight, and then come in the next morning to a working new behavior. To make this level of dexterity possible, every part of the robot platform must be solid, from the hardware all the way up through the entire software stack. One key enabler is providing human teachers with a sense of touch or a haptic teleop device. Also, just like people, we found that robots learn better when they have a sense of touch. And a perfect example of this is the task of flipping a pancake, where the robot has to make contact with a surface it can't see. Without a sense of touch, it struggles and performs poorly, but is successful in learning the skill once it's able to feel its interaction with the environment.
This is only the beginning. Our team is deeply focused on achieving large behavior models that I mentioned earlier. We anticipate the next breakthrough will be when we've trained the robots with enough dexterous skills that they're able to generalize, performing a new skill that they've never been taught. To realize this, we're building a diverse curriculum for robot learning, essentially a kindergarten for robots, to teach them numerous foundational skills that are useful for working alongside people. We're on pace to teach hundreds of new behaviors by the end of the year and over 1,000 by the end of 2024. We're also leveraging our expertise in simulation to augment our real-world teaching. And finally, we're developing fundamental tools for fleet learning so that when one robot learns, they all learn. I've been working in robotics research for a long time now. The tasks that I'm watching these robots perform are simply amazing. Even a year ago, I would not have predicted we were this close to this level of dexterity. And the rate at which we're able to teach new skills is simply astounding. Nearly every day, I wake up to a new message showing the robot doing something it couldn't do the day before. This is an incredible time to be a roboticist.
Okay. Unless anybody wants to see the caramel creme brulee or caramel brulee latte advertisement. How about one more and then we'll take a break?
I wonder what the time's going to be.
What are we about to watch?
What the hell? Oh my god. Look at this shit here.
That is beautiful. One day, I dream I can achieve that. Damn.
You know that's not human.
Man. Insanity. I
don't even know what I just
so
watched.
happy to see that in person. That is like, do you have a vision of what's possible?
You just said that there.
5'3".
What is the laptop? What do you guess?
5'3".
5'3".
5'3" it did.
Okay.
That's pretty amazing, isn't it, Lloyd? And it's
Yeah.
good to know that that will never be used for anything bad.
Sure.
Right. I mean, what could go wrong?
Make your EMP weapons now, folks.
Yep. And put him on a drone.
And put 'em-
You're gonna have to chase the other guy.
I was at a conference back in, I think it was about 2020, and they were having the same kind of competition, and they weren't quite that fast at that time, but man, I'll tell you, the guys that won the competition, it was pretty damn fast. It was pretty good.
Okay, we'll tell you what, let's do a 10-minute break. I will keep the video running and I'll share a timer for us. I'm going to go get a little water and get myself set up for the next segment of this. And we'll come back from there. That sound good to everyone?
Yep.
All right, let me find my timer.
While we're on break, I posted some video links in the chat. The one about the Disney walking robots. If you haven't seen that, it's really worth checking out. They are amazingly cute, and it's a positive video to wash all the darkness out of your mouth.
Okay, there's a 10-minute timer. We'll be back in just a little bit. Oh, actually, I haven't shared it yet. Hang on.
Weekend you went off, or 2 weeks ago. Oh, it was Sunday when you went up to Vancouver. How did you talk about Canada? Okay. Oh.
Okay, I'm back.
Okay. Meeting part 2.
Yep, we are.
Meeting part 2. Yep.
Hello out there.
Another hour.
Yeah, this presentation will probably be half an hour, 45 minutes. It's not super long. There's a little discussion time at the end too, so we'll see where we go.
Somebody's excited.
Hey, real quick, folks. Well, we've got 10 seconds left. Are folks interested? I'm going to do a CUDA talk for the NWCPP group. Are folks interested in that here as well? Is that something that's interesting to this group?
What was the talk about?
CUDA. So this is basically it'll basically be a very quick introduction to how to program, run programs on the GPU.
Yes, that would be very interesting.
Okay. I will, when I do that talk, I will make it dual use.
Yeah, absolutely very interested in that.
Okay, sweet.
I'm just right at that point right now where I'm going to start doing that. And so, yeah, something like that would be very, very interesting.
Okay, I will shoot for that next year. How's that?
Oh, do we have to wait that long? Especially, if you cover like the differences between like standard CPUs, GPUs, and FPGAs. I have yet to hear a really good, concise.
Oh. Oops.
So one of the other things that Intel
Okay, I can
has
do
now is a set of software called Cycle, SYCLE, which is supposed to take over from CUDA, do it better.
Oh, yeah. Yep. I might have had somebody talk on that in the Northwest C++ users group.
Oh.
So, because I think they call it SYCLE, if I remember right.
Yeah.
SYCLE. Yeah.
Yeah.
Yeah. Take a look at if you want to talk on that. I put it in the chat. Take a look at the Northwest C++ users group site. I know I've had at least one talk on that in the last couple of years. And I'm going to take a note. Might be time to see if they can give us an update on that too. Okay, with that, I'll go ahead and get us going on the presentation. We have a really great presenter today. It's me. That's a shameless self-plug. All right, just kidding. I think this is the first one I've ever introduced myself where I've actually run the meeting and done the presentation at the same time. So with that, I'm just going to hand it over to myself like I normally do and get going. Let's see here. Okay, does that look good for everyone? Okay, so this talk is basically, should have a question mark on there, but asking a question. What have we lost? So as technology and software development techniques have moved forward, we've left behind some of the simpler stuff that, it's still useful. I work in an environment where I've got, a fair number of more senior people like myself and a fair number of us on this call or on this meeting. But I also work with a lot of younger kids who have come up where memory, processing power, not a problem, right? A lot of us grew up in a time where kilobytes of memory was considered a luxury. Folks today grow up in a world where gigabytes of memory is considered normal. You don't have, multi-megahertz CPUs, you have multi-gigahertz CPUs and plenty of them. And that really affects how software development is done. So what I'm going to do is I'm basically just going to go through a set of these techniques that I've come across over the past few years. These are all from real world scenarios. In many cases, I won't be able to talk about the full detail of where these came from or how they were used in my case. but they're all real world scenarios that I came across. And one of the things I do when working with teams is I tend to pair up a more junior developer with a more senior developer. That's kind of my philosophy. I do that with myself as well, as often as I can. The senior developer has, a lot more of the, judgment and scope and discipline. But, not necessarily up to date on the latest development techniques, where the junior developer is usually a lot more gung-ho, let's just try it, and is up to date on the development techniques. So a lot of these came out of that paradigm. At the end, I'll have a little bit of time and, folks can share some of their own experiences. So the first one is link time overlays, and all these are going to follow the same general approach. A description, modern day approach, and kind of a quick short how-to. So link time overlays came from a long, long time ago when memory was very scarce. What you did is you loaded your program, and at link time, it could dynamically reload parts of the program. We can the modern approach today is dynamically linked libraries, where it's actually used more for configuration, not necessarily so much for pulling different parts of the program into memory, replacing chunks of memory that you're actually executing against. The trick with this is basically setting a linker command for GCC. It's called allow multiple definition. And then what happens is individual functions or symbols can be replaced based on the link order. Let's see here. Okay. The whole idea of this is to create a duplicate function where each function is in a different compilation unit. And then you can adjust your build to include or not include the alternate definition. So in the case I was using this for, it was used specifically where we needed to ensure we were not allowed to use conditional compilation. Let me just start with that. Okay, so this was a qualification exercise. You're not supposed to use conditional compilation because that executes, or that sets up branching in your program that you can't qualify. But yet you needed to mock certain parts of the system and guarantee that you preserved certain parts of the system for the qualification exercise. So what we did is link time overlays. We replaced a couple of key functions in the system with our own instrumented functions that allowed us to grab onto and ignore information that we needed to get at during testing. So the advantages of this technique, it allows for common code base to be modified for testing while guaranteeing, and that's really important, you're guaranteeing the integrity of the rest of the program. Okay, so you're modifying part of it, and the parts that you do not modify are guaranteed to be exactly as they are in production. In our case, as I mentioned, we were using this to pass a formal qualification, and the exact code used in production had to be modified, but certain parts of it had to be preserved, and we had to be sure of exactly what was modified and what was preserved. The linkage is static, and minimal modifications are needed to the program, so you don't need to put in any conditional compilation. You do all this at compile time, and essentially by building, if you do build, debug, build, release, that's how you control it. And then it's basically in the build system where it can be inspected and reproduced. The disadvantages, this technique is really obscure. Most people have kind of forgotten about it. Duplicate function names are really not expected, and that misleads folks. So when we did this, I had to go explain to a lot of people of, look, this is what we're doing. This is why we're doing it. Okay. And in our case, it was seen as, hey, this is a good approach. But if you don't really need it, it's generally going to be frowned upon. So that's link time overlays. This one is CSV files and simple formats. So essentially using only the simplest file format needed to represent the information. What's typically done today is markup languages such as JSON, XML, YAML, there's tons of these, are used where you have the data elements are labeled. So it's the new the more modern formats are easily human readable. They're self-describing, they're self-documenting. But in doing so, there's a lot of overhead in the file. For a CSV file, it's comma-separated values. It's just what it sounds like. Field 1, field 2, field 3, separated by commas. And then you just write them out. And you can, you write multiple lines. I'm sure we've all seen this. They're very easy to put into, pull into Excel spreadsheets and work with. I've seen some importing for JSONs and stuff now too. The key is size and performance on this. So you can also use a binary format if they're really critical, and we'll talk about that in a moment. For CSV files, simple, regular data. It's easy to read and write in code. If you're working in C, it's printf, scanf, strtoc, or similar. It removes the need to pull in a serialization or deserialization library. So if you're using the more modern formats, they're actually a lot more work to parse. You've got opening and closing delimiters or braces, curly braces, etc., that need to match up. Those can be messed up in the syntax. They're hierarchical. So you can do a lot more things with the modern formats, but they're a lot more work to parse. The files, a CSV file is much smaller than the resulting JSON or XML type file. The redundant field names and delimiters are removed. This can easily interop with a spreadsheet, so it's real easy to read this stuff in, write it out in a spreadsheet. And as I mentioned, binary files can be even smaller. Disadvantages: not as human readable, not as usable where the data structure varies. You really want a constant data structure to do this. There's no error detection really at all, but you do need to write a little custom code to parse. So for instance, with JSON, if you're working in Java or like a JavaScript, you can just pull in a JSON and it'll create the object in memory for you directly. You don't get to do that with the CSV files. You have to do that all yourself. Okay. Simple serial protocols. Excuse me. This is basically the same idea we just discussed, but storing the instead of storing the information to disk, we're going to send it over a serial link, which could be cabled or wireless. Again, much more complex formats such as JSON or XML tend to get embedded inside of a TCP/IP type packet. There's a lot of advantages to doing that. Again, it's readable, it's portable. TCP/IP or even UDP gives you error detection and in some cases correction with TCP. But sometimes you don't need all that. So essentially where you're going to want to use these simple serial protocols are cases where efficiency is critically important. And you generally want to build a packet with the following properties to give yourself some error detection and correction. A clear start of packet message or indicator for framing, clear end of packet message for framing, okay? And some type of error detection. So in the packet I've got listed below, STX is a start of transmission or start of packet flag. That's it's an ASCII byte. And then you can put in your payload, which in this case is the bytes 1 and 2. And then the third byte is a checksum, very simple. just add them together, and then you flag the end of packet. Even though the start of transmission and end of transmission bytes could show up inside the packet, when you frame them this way and you take an entire packet, you can still get a proper framing. It's unlikely that you'll get an STX inside the packet with an ETX in the right correct position and the proper checksum, so you can adjust for that. It is some work. The advantages can be optimized and tuned for the specific application. So this is from a real example. I'm going to make it up a little bit. But let's say you have an example where you want to send the X and Y coordinates, and they're going to range from 0 to 99 inclusive. Okay, so you're just basically sending a stream of bytes where a packet is 2 bytes long, and you just want to send a coordinate 0 to 100 on 2 axes. So we can do that with 2 bytes. In this particular case, we're going to flag, say, the X coordinate by setting its high bit. So essentially, you're using that bit to tell which one is the high byte or which one is the low byte. This particular application, it did not matter if you lost a packet or if you lost a packet or if a packet got corrupted. Essentially, in this particular application, you were just trying to send updates as quickly, as simply as possible. If a bad update got in or an update got missed, the one right behind it would correct it. So by having the high bit set, you know exactly which byte is X, you know exactly which byte is Y, and you just update as fast as possible. The folks that I was working with at this point, we're actually using a JSON packet to do this work. And if you look at the example below, the JSON packet's about 20 bytes, depending on your white space and just where you put, commas and spaces and so forth. By sending 2 bytes, we were able to speed that transmission up by a factor of 10x. It also made the parsing much, much more simple. You just grab a byte, check the high bit, you know which one it is. You don't have to worry about trying to match up curly braces, trying to convert decimal characters back into an integer. So essentially, in addition to speeding up the serial transmission, this was a fairly low bandwidth link, it also cut down on the computation required to form and decode the packet on both sides, which was also really important. This was a battery-powered application. It was trying to use very simple processors, but be as quick as possible. Disadvantages, not as easily human readable. You're not going to get it parsed by protocol analyzers. You can write your own in some cases. You do have to write custom code on both sides to match with the data contents, but you're sending simple data, so this is simple. Complex or variable data, again, becomes much harder to work with. So let's combine that with simple serial ports. So a lot of us are familiar with the RS-232, 422, and 485 ports. These are simple 2 to 9 wire serial ports. They've been around for decades. They're still everywhere. But now they tend to be just simple use cases. Most applications today tend to use Ethernet for long distances and USB for short distances. So you can still actually purchase a PCI card that's available that supports RS-232, 422, and 485. You can use a USB to serial adapter. Depending on your application, the PCI card, if you can go that route, is actually a better choice. It's a little more expensive, and then you got to open the box and plug it in. But with USB, you can get additional jitter and latencies and so forth because of the USB protocol. So depending on exactly what you're doing, be aware of that. There's also chipsets. FTDI is the most common, and it's widely supported by all the major operating systems. If you're using a USB to serial converter, I always try to look and see if the chipset's FTDI. I would really recommend that. I've had very good luck with them in the past. You can also get Ethernet to RS-232, 422, 485. I've used those in the past, and for certain applications, they're very helpful as well. In the code, you just simply open the serial port, typically as a file on Linux. It's a little more work on Windows. But insert play reading to it and writing to it. Either in the operating system or in a particular call, you do still need to set your baud rate. So the advantage of simple serial ports, they're simple to use, and you get fine-grained control. You get very good control of exactly what's going over the wire and at what time. You're almost directly on the wire with your software. The software stack is much reduced compared to a Ethernet or a USB stack. They can be extremely robust to environmental influences, and the chipsets can also be radiation hardened, which for some of the stuff I do is kind of important. You can also connect directly to very simple microcontrollers like Arduinos and hardware devices, and your latency is very well defined. Furthermore, you can build, if you need much tighter latency, and some applications do for timing and control, you have direct control of that by when you send the packet. So you can build your own protocol to engineer that latency and the timing exactly the way you need to. Disadvantages. You have to code up your own networking stack. Okay, so if you're going to do anything complicated, you're kind of responsible for that yourself. The baud rates are typically low by today's standards. I think I've seen faster, but they tend to max out about one megabit per second. But that's not too bad. The range is limited by today's standards. These are simple. In the case of RS-232, it's plus or minus 12 volts ground referenced. RS-422, 485 are a differential signal. You're going to go tens to hundreds of feet with these, but you're not going to go much over that. The cabling can also be heavy by today's standards. None of these are as lightweight as, say, like a fiber optic. Okay, this one's actually one of my favorites. Stream processing of a file. So I've seen this one multiple times. It's basically the idea is you treat the file like a set of information packets, reading one packet at a time and processing it. The modern day approach is reading the entire file into memory and then processing it as a big array. The first time I wandered across this, one of the younger folks I was working with came to me and it's like, yeah, I'm having trouble getting the performance I want out of we were reading a big set of data coming in from a test run. And the file was about 1 gigabyte in size. And it was taking almost as long to read the file and process it as it did to generate the file, which, considering it was coming from hardware, was really, really slow. So he came up and it's like, yeah, I'm trying to, I'm not getting good performance on this, pulling this file in. And I asked him, okay, so how big is the file? It's 1 gigabyte. Okay, how are you reading it? Well, I read the whole file into memory, and then it's like, you're doing what? Never even occurred to me you would do this. There's some definite advantages and disadvantages to doing this, which we'll get to in a moment. Basically, though, if you're going to stream process the file, and this is kind of the more modern term for it, it's almost become kind of a specialty. To think about stream processing a file, where in the past this is the only way you did it because, hey, we didn't have 1 gig of RAM to read the whole thing in. Basically, what you do is you open the file just like you would, but instead of reading the entire file into memory, you take in one work unit. Okay, and work unit, think of like a network packet. Depending on the format, it may be constant data. So I'm just going to read the first 124 bytes, and that's my packet. Or maybe I have to read a byte, and that will tell me how much to read. But I'm only going to grab one work unit of data. And then I'm going to process that work unit, and then take the next work unit. And I'm just going to keep reading the file and processing work units until I get to the end of the file. So at no time do I have more than one or maybe two work units in process at a time. In most cases, the code ends up being no more complex than working from memory, but it is different. So even if you're going to pull the entire file in, if you have a variable packet size, you still have to go in and parse that in memory. The only difference is it's an array index instead of a read from disk. Another advantage, the resulting code can be used on any type of stream, including a network socket. So this is something I found very handy in the past, that I can basically, once I get the code written this way, I can write the file to disk, I can read it from a network socket, and with the exception of having my underlying reading routine, taking from different sources, the actual packet processing so forth is identical. So essentially, I get replay capability for free once I do this. You also get some parallelism for free. If you're reading from a disk, the operating system is going to read ahead and cache the next set of bytes for you automatically. So you don't have to manage separate threads for a read thread and a processing thread. So while you're processing one packet, the operating system has already pulled the next packet into a memory buffer for you. And that simplifies your code. You can also handle file sizes or files of any size, including live streams. Okay, disadvantages. If you have a file format that requires random access, this is actually harder in some cases. You can always do like an LC and reposition your file pointer. But it's more complicated than just grabbing the index and dereferencing it. And some parsing operations, you'll actually need to put a little state machine in. And that can be harder in some cases. Okay, so another one of my favorites, blinking an LED and a debug GPIO. So description, just configure a GPIO line as an output and toggle it from within your code. This is really effective during board bring up time, so when you're trying to bring new hardware up. What people tend to do today is the first thing they bring up is the JTAG. And you have to do a little bit of that anyway to even get your code in. And or they bring up the serial debug port on the device. These are much, much more complicated interfaces. So essentially what you do is start by constructing an absolute minimum program. Okay, just bring the program up, initialize your memory controller if you need to, something like that. Initialize one single GPIO line or port, whichever is simpler. And then just put yourself in a loop and toggle it high and low. Now, depending on the speed of your device, you may need a delay in there as well. If you're toggling so fast that you're putting out hundreds of megahertz on this GPIO line, you're going to have trouble reading it with a scope. And then finally, you just monitor the state of the output line with a scope, logic analyzer, or even a low power LED. Exact circuit depends on the hardware you're going to use. Advantages. This is really, really simple to get working compared to other approaches. If you have, one of the cases I ran into, took the person several days. They were debugging, and essentially they were getting their JTAG up, but the minute they started running the program, it would crash. Turns out they had not configured their watchdog timer, and essentially the minute they started running the watchdog timer, hit the reset, took down the JTAG and everything else. We were able to do this and say, hey, wait a minute, the program's actually running. What's taking it down? So that's where this particular slide set came from. There's extremely low latency on the GPIO line. It's with most systems, it's with 1 or 2 instructions. If you're debugging a timing issue, that's critical. GDB or various forms of JTAG or serial port debugging won't give you the timing resolution you can do with a debug GPIO. You can do multiple lines and put out individual numbers for individual state. Talked about the watchdog example. And this is, this used to be the standard first test when you bring up a new board. It's, blink an LED. And now it's, can you get your JTAG and your debugging port up and running? It does require some external hardware to monitor, and it requires some basic electronics knowledge to be set up. Your information can also be fairly limited in what you can send, but for certain types of information, this is critical. One of my best practices when I do any type of hardware design is I've always got at least one 8-bit port somewhere in the design where I can, I can set this up at a later time and send out state information. These days I end up having to come into projects and stuff, and I usually end up setting this up for people, and then they're kind of like, oh, that's simple. So it's another one of these techniques that's been forgotten. Bare metal coding. Basically, it's creating your application directly against the hardware without using a framework or operating system. Modern day approaches use a small ARM processor and put Linux on it. That really brings up your startup time a lot. And sometimes, especially for some small processors, you really don't need everything Linux provides. My favorite pet peeve here is I have one of the Belkin home automation light switches in my place. And when I got it, like, oh, this is cool. I can go through, in our case, we were using Google Home. And, I can say, hey, turn on the lights. And I'm not going to say the command, but, turn on the lights, turn off the lights with a voice command. And essentially what I discovered with this is when you do that, it's going out to a server. The amount of complexity involved is crazy. It goes through your Google Home device. It sends it to one server that decodes that into a text string for operation. That comes back. It goes to another server that then echoes it back to your Wi-Fi enabled light switch. So it can actually take several seconds for this to occur. The thing that I found most annoying is the light switch is actually running Linux. And if we have a power failure, that light switch takes about 20 seconds to reboot. So they didn't actually optimize the boot time of their Linux either. It allowed them to create a product very, very quickly and simply, but not very well optimized. Essentially, for bare metal coding, though, what you want to do is create a description of what you're trying to do your requirements. If the application is simple or has hard real-time requirements, consider working directly against the hardware or with a very, very light operating system. And the exact details are going to vary depending on exactly what you're trying to do. You can implement more hard real-time applications by doing this. In many cases, the development can be simpler and faster if you're not trying to customize and bring up a Linux system on your little microcontroller. You can use a smaller microcontroller with much, much simpler hardware and still get the job done. That's going to allow for lower cost hardware. It's going to improve your power consumption. As I mentioned, it's going to drastically improve your boot time. You can get fine-grained access to the control without having to do your own drivers. And then one of the tricks I use is one of the things you come back, it's like, but I need multi-threading. A lot of times your multi-threading is really to deal with multiple hardware devices. You can use the interrupts and the DMA engines to simulate a multi-threaded application, and you actually improve your performance when you do that. In some cases, it may require more coding to implement your device drivers, and I've got that in quotes. It's not really a device driver. You're just going against the hardware registers. Your development and debugging tools are more limited, and you're going to be doing embedded systems development by its very nature. So you're not going to be able to pretend you're on a desktop and just drop your app into your little Linux world and have it run. Okay, hand optimized functions. So this one actually came from a book I was reading in C++ land talking about performance in C++. And what they did was they actually kind of trashed the standard library a little bit. But the takeaway is, in some cases, creating a dedicated function that does only what you need to do in place of using traditional library function can be beneficial. The modern day approach is, I need to do something. Where's the library that does this for me? And you pull in a whole library. There's advantages to that too. The pulling in the library is typically the quickest thing to do, but if you're performance constrained, the library is typically a general solution to a general problem, and it's going to carry overhead that you may or may not need. So first, consider what's really special about what you need to do. Do you really, really have something that's special, or do you just have a general case thing where the library will be fine? Most cases, just go get the off-the-shelf library and use it. Okay, I don't want to be advocating, replacing well-tested, commonly used libraries for just general stuff. Okay, so that should always be your first cut. Go get the standard off-the-shelf thing, especially, and just try it. Now, you can profile and evaluate the available libraries. And if they don't work for you, now you're starting to move down this, okay, should I do this myself? The work you do in profiling and evaluating the general libraries is also going to guide what is special about your application or your use case. So before you go build something new, make sure you know what you're building and why you're building it and what's special about it. That will guide your design. Go ask a friend or a coworker to get a second, third, or fourth opinion. Make sure you're going down the right path and you just haven't missed something. I've had multiple times where I've like, oh, I need something special here. And I go ask a coworker, it's like, oh yeah, this will do it for you. I just didn't happen to know about it. There's so many of these now. Nobody knows, all of them. The key is to make sure you know why the existing solution is not going to work for you and have some idea of how to improve it. So if you just know, this isn't going to work for me, that's too slow, it takes too much memory, it requires some type of resource I don't have, you need to know why the existing solution doesn't work before you're going to be able to make something better. So if you've made it to that point, you know what you need to do, how you're going to do it, try to code it up and make sure it works better for you. The advantages will be, it'll be completely tailored to exactly what you need to do. And you're not going to have anything, any additional overhead that you need to worry about. You also might come up with a better way of doing something that just hasn't been done before. I've seen several cases of this where, oh, I need to do this for a particular use case. And you go through a whole lot of work. This is going to take considerably more time to develop, debug, and maintain. But, you may find something that's like, oh, this can be brought back into a general purpose library and improve that as well. You may spend a lot of time attempting to develop the solution, only to find out it's not any better. Okay, sometimes there really are just hard limits and you have to go do something else. And your coworkers are always going to make you justify why you did it yourself. If I get a code review and somebody does this, first question is, why? Sometimes they give me a good answer, sometimes they don't. But you should, the minute you go down this path, you should be expected to answer the question, why did you do it this way? Okay, simply installed programs. Basically creating a statically linked program that consists of one file, and everything is in that one file. The modern day approach is you create a whole bunch of files, and then you either create an installer application or wrap everything into a Docker container. I've worked with a couple of groups that couldn't do anything without using Docker. And it's like, this is supposed to be an embedded application. We're not using Docker. Okay, evaluate. So evaluate if a single file is really appropriate for your application. Then put a development process in place to controls the addition of other files, and DLLs, shared libraries, configuration files, registry settings. You should be controlling all that stuff anyway, because you're going to have to put it into an installer even if you don't do this. And then there's many, many ways to embed data into an executable file if needed. I'm going to reference down here a talk that was given by Jason Turner. I believe this was at CPPCon 2022. Could have the year wrong. But anyway, there's the link, and it's called The Power of Compile Time Resources. He goes through a whole set of techniques to embed just about anything you want into a C++ executable or C++ program. The other trick you can do is on the first run, the single executable can set up your registry settings, create databases, anything you need to. You just basically code it into the program. If it's not there, program just creates it on the fly. I've also used that for updating programs. The advantages, the application is easily moved around. There's no installer needed, with a small disclaimer of you may need to actually put some installer type code into your program. There's no dependencies, no DLL hell, everything's self-contained. Application development can be simpler in some cases. Some cases it's a little more complicated. And application performance can actually be faster in some cases. You're not reaching across a DLL or thunking or some of the various other things that happen when you have pieces in different locations. Disadvantages. The architecture of the application is going to be limited. You just can't break down an application and modularize it the way you can if you have modules, right? It's a direct conflict there. You either have modules or you don't. You get one advantage or the other. If you're going to update the application, the whole application needs to be replaced. If the application's, a couple megs or even 100 meg, that's probably not a big deal. If your application is gigabytes in size, that could be a big deal. Sometimes you may or may not be able to package a dependency that you need into the executable. Something like a video clip, for instance. You probably could do it, but it's probably going to be awkward. Okay, and finally, last but not least, we talked about this last month. James Newton and I, thank you, James, got talking about this before the talk last month, and I actually had one of these when I was a kid. This is actually what got me into software engineering. I'm a great fan of these things. It's the cardiac computer. And what you're looking at is a picture of the actual computer. This was a teaching aid. My dad was taking a class through Boeing where he was learning Fortran. And this was in the learning set that he had. And I kind of globbed onto this thing as a child and started programming it, quote unquote, programming it. It's essentially a computer made from cardboard. Simulates all the operations of a very simple CPU. And what you're looking at on the left-hand side is essentially a set of cardboard sliders that are simulating the various multiplexers in the ALU and various other operations of the computer. So the left-hand side is essentially an accumulator. The right-hand side is essentially your memory. It's got a little set of opcodes. You put the opcode in, and in doing so, it sets all the sliders properly to carry out that opcode. Absolutely beautiful mechanism for showing how a computer works, and actually getting the student, which in this case was me, involved in actually doing the work the computer would do. I haven't seen anything better at how you simulate or teach this since. But James actually went ahead and developed a little website that does something very similar. You can put the opcodes in, and yeah, it simulates this thing. So not quite as good as moving the sliders around, at least in my mind. But he's got cardiac reborn. So with that, I'd like to turn this over for a general Q&A, open discussion. We've got about 15-20 minutes-ish left here.
Right.
Yeah. Yep.
So I actually used a cardiac in high school. Do you know what the acronym stands for?
No, I do not.
It is Cardboard Illustrative Aid to Computation.
Oh, cool. Okay.
And did you mention that at least in the version that I used, you used a grease pencil so that it was easily erased, so that you could go make changes.
Oh, okay.
But I don't believe my cardiac had all of those slides. It must have been an older version.
Oh, okay. Yeah.
I'd be interested in seeing how all of those little slides work. That looks like it's more fun.
Yeah, they're really cool. The version that I had, I actually put there was Scotch tape available at the time that had a rough surface. So actually what I did is over all the writable areas, I laid down a layer of the Scotch tape, and then I could write on the Scotch tape with just a regular pencil and erase it without wearing out the cardboard underneath.
Right. So, but the way it came, you were supposed to use a grease pencil, and it had that finish that you needed so that you could easily wipe it off.
Okay. I don't think the one I had that. So interesting. So there's multiple versions of this thing running around out there. That's actually kind of fun.
So it worked with 2-digit decimal numbers.
Yeah.
And so I wrote a Fortran program to simulate it, but I used binary so that I was able to have 2 hex digits, and as a result, I could add instructions to the instruction set. So it had all 10 instructions, so I needed more. I needed IO and various other things. So that was fun.
So just to throw this out there, another really wonderful resource for learning like how computers work at that level is NAND Game. If you haven't seen nandgame.com, just a wonderful, wonderful starting point. Starts off with relays and walks you through digital logic up to the point of actually having a computer program. And then I think cardiac, maybe, I don't think the order is important, but what cardiac gives you is this idea that program operations are numbers, right? And that seriously seems to really be missing in a lot of even college educated programmers. They like, oh well, it's executing this text that I wrote. No, it's not. It's executing a number.
Right.
And just the idea that the fields in the number, which in the cardiac are the digits of the number, can have different meanings. Like the first digit being the instruction, and then remaining digits being an address or something like that. There's so many really important concepts in that that I think a lot of it. There's 2 sides to it that I think are important, and that's why I really appreciate this talk and going through all of these details. Is the first side to it is that you don't understand what's really going on, and so maybe in some rare case you might not understand what's going wrong or how to solve the problem because you don't understand the actual underlying technology. But I think the bigger loss is when you do understand the underlying technology, you have a mental framework upon which to hang new information as you learn it. It gives you a structure to build upon that you don't have if you just start memorizing Python programming, right from the start. I think that structure being missing in the educational system for programmers and for other technical people is really a huge loss.
Yeah, I'm going to jump onto that one real quick. 'Cause the big thing I took away from playing with Cardiac was I'm going to go one step further than you did, James. You're executing numbers, right? But those numbers are actually directing data flow inside the processor, and it is that data flow that is responsible for carrying out the work. You're taking
Exactly.
Yeah, you're taking two registers, you're feeding those registers to an ALU, and the output of that ALU goes to another register. It's not just, hey, I put two numbers in and magically got added and I got a third number. It's like, no, there's machinery under this that is quantifiable, it's understandable, it's predictable, and it's making all this happen based on what you told it to do. You're really, when you're coding, you're really setting these registers and so forth. And certain types of work, like I've done talks on the Cypress PSOC, for instance, certain levels of work in there, you have the universal digital block, for instance. You have exactly this. You have an ALU wrapped by a couple of CPLDs, and you can make up your own instructions. Guess what? When I got to doing that decades later, that being able to understand how that data flow is controlled by an instruction that I learned from this Cardiac made that so much easier than anybody around me.
That is such a great point, Lloyd. This is the thing where you realize that because it's a number, now it can be used to address different registers or enable different circuits or whatever. It's really the glue that holds the digital logic to the actual software or the programming. And not understand it really makes me sad for kids who are learning how to program today, that they don't have this structure or this fundamental to build upon. And so when you see them floundering, when you see them saying, oh, this is too complicated, I can't learn it or whatever, it just breaks my heart, because I understand in part that this is why they can't understand it, because it hasn't been explained to them correctly.
Yeah, and they don't have a hands-on tool today. So let me take it to one more dimension. So I work with people both in hardware and software. To the hardware folks, blinking an LED from code is no big deal. And for most of us here, we're in robotics, the whole concept of code controlling hardware, we're pretty comfortable with that. People who work in a pure software world, where they don't know about GPIO lines or things like that, the concept that you can change a 0 to a 1, and that can flip a hardware line and have an effect in the real world. That's just magic to a lot of people. And it's like, it's a very simple concept once you get taken through what's really happening. But there's a lot of pieces you have to go through to get there.
So what you're talking about is learning assembly language programming.
Not even necessarily learning assembly language, but learning how data is represented and how data flows through the computer.
Yeah, and if you learn assembly language, you understand that very well.
Yeah, learning assembly would be one mechanism to do it. But
I do think learning assembly is important, but and maybe just if you learn assembly and then you said something like, hey, each one of these assembly language instructions that I'm writing out is not a piece of text. It turns into a number once it gets inside the computer. If they can just get that concept. So I mean, like I said, my levels would be like, I would start off with an understanding of atoms and how they're spaced out, and how the spacing of the atoms through ionic bonding causes the valence electrons to be able to move from one,
okay, you're going really low level, James.
right, exactly.
Yeah,
but
to be fair, you can only learn so much in a given degrees amount of years, and so the question is, do you want people to be able to derive Maxwell's equations from first principles and
Well,
learn
no.
materials for some, or do these people want to learn enough in their 4 years so that they can write a video game and retire a millionaire by the time they're 22?
But the point is that you can hit these concepts at a high level, right? Like you can understand how electrons flow through a wire, and then you can understand a little bit about semiconductors and about how transistors are switches, and then you can understand digital logic, and then you can play NAND game and see how the computer gets built up, and you can play with cardiac and understand how numbers can be used to program. And then, I think I would follow Bob's suggestion and learn a little bit of assembly language programming, not a lot, just enough to understand that the assembly code gets translated into numbers. By the way, have to mention Kathleen Booth wrote the first assembly language. The first thing that ever translated assembly language into a machine language was invented by her, and she just died about 3 years ago, something like that. Had a good long life in computing. And then after assembly, like C, and then on up into higher level languages. The point I'm making here is you have to understand all of it. You have to understand all the different levels, and you don't have to understand any one level to a tremendous degree. But without having that structure, that bare bones structure to hang things on, the information doesn't click in the way it would if you had that. Does that make sense?
Yeah, but it depends what your goal is, right? If your goal is to understand things at a doctor of philosophy level, then yeah, you should definitely understand things all up and down the stack. But if your goal is to make a very lucrative living, then people may not care, what goes on with, in an ALU. They care, how can I get a job done and turn it into a big paycheck?
Yeah, so I'm going to take that one to the next level a little bit. If you understand this, you actually have a better chance of, turning it into a good product and making $1 million and off you go, because you're going to have a framework of when you run into a problem, you don't necessarily know all the details of what's going on, but you know enough to go outside the scope of what you know and research it. So one of them I typically run into, I tend to work hardware and software a fair amount, back and forth. I've run into multiple teams, and this usually starts on the software side because they don't have the underlying experience, where the software team finds a bug. So they have a bug that's being exhibited, and they get stuck in the software world trying to solve it. So at one point we were working with it was a USB-based debugging system, right? And everything seemed to work fine, but the debugger kept going down. And the debugger team was literally on the order of 10 people, spent months trying to find and fix the debugger issue, because they assumed it was a software problem. What really turned out to be happening, and I actually found it kind of by chance. I wasn't even really working on this. I was working on a power management issue. But what I noticed is when the voltage on the USB port was low, and I was controlling this directly, this was part of the work I was doing, the USB would disconnect. I'm still within USB spec, but when I was at the low end of the voltage scale, my USB would just go down. And I was seeing the same thing. And I was lucky enough to have all the tools in front of me to to actually play with this. But the problem was it wasn't a software issue. The problem was they had there's two resistors on the USB bus that essentially they're loading it. They're controlling ringing and various other electrical characteristics. They were just wrong. And we took the device, stick it on a USB scope, did a what's called an eye test, and basically because I had the right tools and a broad enough knowledge to say, hey, this could come from different areas. I was able to see that the problem was actually a hardware problem that just manifested in software. And that's the piece that's missing. You get everybody kind of into their own little world, and that's all they can see. They don't necessarily know what the framework is out. I'm not a USB expert. I had to go get somebody to help with that, but I at least knew enough to identify it and take it that next step.
I have to, let me add on to what you said, Lloyd, and also say, I think that today you could not even learn how to program in Python, but just, get an account at OpenAI and ask ChatGPT to write you a Python program or a website and make $1 million. If you are lucky and you have the right idea at the right time and you attract the right investors. And, I think there's a lot of talent involved in making money, but it's a completely, that's a different specialization. But here's the key for me, okay? You have to get lucky for that to work, right?
Yeah.
When it doesn't work, then you need a guy like Lloyd who kind of knows a little bit of everything and can point you in the right direction to fix it, right? So that's, and it's all about what you want to be and what your goals are. If your goals are making money, great. That's nothing wrong with that. God, I love money myself. But, what I derive a lot of my pride from personally is not that I make a lot of money, because I make okay money, but I'm not rich. What I derive a lot of my pride from is that I can figure out what the heck is going wrong. I'm a fantastic troubleshooter. And it's because I understand how things actually work underneath the hood.
Yeah, and if you're going to be designing and building robots, God, you need all of that.
Yeah. Yep. So, folks, I'm going to have to bring this one to a little bit of a close. I do have a hard stop today. Does anybody, everyone is welcome to continue chatting. Does anyone, first, does anybody want to do that? And second, who would like to take over as the meeting owner just to close the meeting down at the tail end? I'm going to stop the recording at this point.